Imagine studying for an exam. One student memorizes every single question from last year's paper. Another barely studies at all. Now the real exam arrives. The first student panics because the questions are different. The second student also fails because they never understood the material. Surprisingly, AI makes these exact same mistakes. Sometimes it memorizes too much. Sometimes it learns too little. And finding the perfect balance is one of the hardest problems in machine learning. Today, we're going to understand why AI sometimes becomes too smart for its own good, and why sometimes it's simply not smart enough. By the end of this video, you'll understand concepts that every AI engineer deals with daily, from chatbots to self-driving cars. What does learning actually mean? Before talking about overfitting, we first need to understand what learning means. Imagine teaching a child what a cat looks like. You show 500 different cats. Some are black, some are white. Some are fluffy, some have long tails. The child eventually learns the general idea of cat. Now show a completely new cat. If they say, "That's a cat," they've generalized. That's exactly what machine learning tries to do. A machine learning model doesn't need to memorize every picture. Instead, it tries to discover patterns that work for images it has never seen before. This ability is called generalization. Generalization, not memorization, is the real goal of AI. Training versus testing. Think of training like practice questions. Testing is the real exam. During training, the model adjusts millions or even billions of internal parameters to reduce mistakes. The model repeatedly makes predictions, compares them with the correct answers, calculates the error, adjusts its parameters. This process happens thousands or even millions of times. Eventually, the training error becomes smaller. But here's the catch. A low training error doesn't necessarily mean the AI is actually intelligent. The only thing that matters is how well it performs on new, unseen data. That's why machine learning splits data into training set, validation set, test set. Think of it as homework, mock exam, final exam. Underfitting. Let's start with the simpler mistake. Underfitting. Imagine trying to predict house prices using only one feature, the color of the front door. Clearly, that's not enough information. The model ignores important factors like location, size, age, nearby schools, transportation. Its predictions are terrible. This is underfitting. The model is too simple. It hasn't learned enough. Technically, underfitting usually happens because the model has insufficient complexity. Training ends too early. Too few features are used. Excessive regularization. You can recognize underfitting because training accuracy is poor. Validation accuracy is also poor. The model performs badly everywhere. Overfitting. The model memorizes the training data instead of learning the underlying patterns. Here's a funny example. Suppose every dog photo in the training set happens to be taken on green grass. The AI secretly learns green grass equals dog. Now someone uploads a dog standing on snow. The AI says, not a dog. Now let's look at the opposite problem. Imagine memorizing every practice exam question. Not the concepts, just the exact answers. You score 100% on practice tests. Then the real exam changes slightly. Suddenly, everything falls apart. That's overfitting. Why? Because it memorized the background instead of learning the dog itself. Overfitting often happens when models are too large, training lasts too long, datasets are too small, datasets contain noise, labels contain mistakes. You'll notice training accuracy becomes extremely high. Validation accuracy stops improving or even gets worse. The AI looks brilliant during training, but disappoints in the real world. To understand this balance, engineers use two important ideas: high bias, high variance. High bias means the model makes overly simple assumptions. This leads to underfitting. High variance means the model reacts too strongly to tiny details in the training data. This leads to overfitting. Imagine drawing a trend line through scattered points. A straight line may ignore obvious patterns. That's high bias. A wildly twisting line passing through every point captures noise instead of the real trend. That's high variance. The goal is finding the Goldilocks zone. Not too simple, not too complex, just right. How engineers prevent overfitting. Modern AI uses several clever techniques. More data. More examples help the model discover genuine patterns instead of memorizing. Data augmentation. Images are rotated, flipped, brightened, zoomed. The AI learns that objects stay the same despite changes. Regularization. Regularization discourages the model from relying too heavily on individual parameters. Think of it as gently telling the AI, don't overreact. Common methods include L1 and L2 regularization, which add a penalty for overly large weights, encouraging simpler models. Dropout. In deep neural networks, dropout randomly disables some neurons during training. This prevents the network from becoming overly dependent on specific connections and encourages more robust learning. Early stopping. Engineers monitor validation performance. Once it stops improving, training stops, even if the training accuracy keeps increasing. Cross-validation. Instead of evaluating on a single train/test split, the data is divided into multiple folds. The model trains and validates several times using different splits, giving a more reliable estimate of how well it generalizes. Why this matters in everyday AI. Every AI system faces this challenge: medical diagnosis, fraud detection, speech recognition, recommendation systems, autonomous vehicles, large language models. If an AI overfits, it may fail when encountering real-world situations it has never seen. If it underfits, it never becomes useful. Every successful AI product balances these two extremes. That balance is what separates research prototypes from reliable, real-world systems. Overfitting and underfitting may sound like technical terms, but they're really about something very human: learning. Learning isn't about memorizing, it's about understanding. The same is true for AI, and every breakthrough in machine learning brings us closer to building systems that truly understand the world, not just remember pieces of it. If you enjoyed this video and want to understand AI beyond the buzzwords, subscribe for a new video every week. because the future belongs to those who understand how intelligent machines really learn.